All right, so one more time. So hopefully this doesn't do it again. There must be a fixed number of trials. Each trial can only have two outcomes that don't have to be 50-50. That can be reduced to two categories. So like rolling a die, one or not one. All right. These outcomes can be considered either a success or a failure. The outcomes of each trial must be independent of each other. So one cannot depend on the other. They have to be independent. So it's either a one or not a one, right? The probability of a success must remain the same for each trial. So no matter how many times I roll the die or flip a coin or do whatever, it's the same odds every single time, right? Any questions on that? So that's what a binomial situation would be. So a success in a binomial experiment is neither good nor bad. A success just means that the result was what the researcher was looking for. For example, multiple choice test is given and the outcomes are either correct or incorrect. If the researcher is looking for the probability of incorrect answers, then an incorrect answer would be considered a success. On the other hand, if the researcher was looking for the probability of correct answers, then a correct answer would be considered success. So let's look at an example here. So classify each of the situation as binomial or not. Roll a standard die 200 times. Not, because there's 6 outcomes here, right? It would have to specify I want this number or not this number. So this is not. Survey 100 shoppers asking for their favorite exercise shoe brand. Not, unless it specifically said either Nike or Adidas. It has to get down to 2 categories. Survey 100 teenagers asking if they play the video game Halo. Yes, right? It's either yes or no. We still play that game? I have it on my Xbox. I just haven't started it because I've been doing the Gears of War. I went back all the way to the first one because that's what I played when I was a kid. Was the first Gears of War. That was 2007. That's when it first came out. Where you could pick up a body and use it as a shield. We used to play Halo a lot, but I wasn't old enough where I played it on a computer. I played it when it was on Xbox 360. But Halo was originally a computer game. Sorry, totally distracted. All right, ask 300 viewers if the recall seen a Coca-Cola commercial during a particular show. Yes, that's what I was kind of going with. I don't think it's going to matter what show it is. Did you see a Did you see a Coca-Cola commercial? Yes or no? So it could be during your SpongeBob, it could be during your Spanish soap operas, whatever you want to do there. So that would be a yes there. Test 4 brands of aspirin to see which brands are effective. No, it would have to be down to either, they would have to change it to it's either effective or not effective, or down to 2 brands. All right, so any questions there on between binomial and not binomial? All right. Just don't do it. All right, so the outcomes of a binomial experiment and the corresponding probabilities of these outcomes are called, what do you think? Binomial distribution. I think my handwriting is only getting worse the more and more I teach. I don't think it's getting better. Can I help you? Yes. All right, so notations used for binomial experiments. Little n will still represent your number of trials, just like as if it was a sample. Your x would be the success, so that would be the result that you got for that certain trial. Then you have a probability of success or a probability of failure, so you only have 2 options. P would be just the number, what's the probability of how many successes you got, so like your frequency. So let's say I did flipped a coin 100 times and I found out that 70 times was a heads and the other one was 30% would have been tails or whatever I just said, right? So that would just be your frequency. To calculate frequency, you could also just figure out one and then subtract it from one to get or however many trials, I guess, really, to find the probability of success. All right, questions? All right, so it says notation, same as always. Then here is your formulas that follow. So some of this kind of comes back from the permutation and combinations, but then has a little bit more going on. So in a binomial experiment, the probability of exactly X successes in N trials is followed by this. You have your N factorial on top, just like in a permutation or a combination. The only difference is you would do N minus your X here. So that would be however many successes you want. So let's say you're trying to get 50 successes out of 100 trials. So that becomes 100 minus 50. And then over here, you would just have your 50. So just like combination, then you would want to multiply of your probability of success, raise how many trials you want, times the probability of your failure with raised to whatever numbers you don't have. So like I said, let's say we're doing 70 successes here. So I would do like 100 trials. And then over here would be like, all right, this would be 100 minus 70. And then times the 70 factorial here. And then I would go, all right, my probability of success, let's say it's flipping a coin, would be 0.5. And I want that to happen 70 times. So I'd raise that to the 70th power times the probability that it fail, which happens to be 50%. But we know that's not always the case. Could then raise to 30%, and then I could calculate my probability of success for that, whatever I'm looking for tails or heads or whatever it is. Does that make a little more sense with numbers? All right. So this is definitely a calculator question because I don't expect you to know 0.5 to the 70th power. You'd be here for a while. All right. And again, that's just coming from that combination formula there. So keep in mind that no successes equals 0 must be considered. So X equals 0 must be considered. So basically just means you flip a coin 100 times and you want tails and you get 100 heads. X equals 0 would be your success. And that can still be an answer. Or vice versa, X equals 1 can be the answer as well. Meaning I flip the coin 100 times, they all end up heads. So that's a 100% probability of success. All right, does that make sense? So basically your answer is still between 0 and 1 or 0 and 100 if you're looking at a percentage. So definitely using technology. All right, so let's look at example 12. It looks like they did most of it for you, or maybe not. Did they? It seems like they did. Oh, well, we'll talk about it. All right, so probability of rolling twos. So we go, here's a 6-sided die is tossed 5 times. A success is a 2, so what's a failure? Not a 2, right? So 1, 3, 4, 5, 6, all of those, right? So a failure is tossing a result that is not a 2. So each toss of the die is independent of other tosses. So if I roll the die, it doesn't affect the next roll. So the probability of my success is 1/6, but my probability of failure would be 5/6 because I'm just trying to get a 2, right? So we find the probability of getting exactly 3 2s. Then part B says find the probability of at least 3 2s, and then find the probability of at most 2s. So here we go. Does it have anything to do with the rest? Oh, on the chart, they did all of them. All right. So you got the chart, right? So we'll just kind of go through that, save us some time. Hopefully we can do one together though. So you don't have to do all of these, but they did the success of all 5 throws, all 5 tosses, right? So that would just be, all right, there's 5 in the trial. I want no 2s to be chosen. So that'd be 5 minus 0 times 0 factorial. I never did look it up. It's still on my to-do list on why 0 factorial is 1. And then here you can see that my success, I want it to happen 0 times, so I'll raise it to the 0 power. My failures, I want it to be 5 minus 0, so I want my failure to be raised to the 5, all trials. And when you type all that in the calculator, you get this. So you have a 40% chance, basically, of not getting any 2s. And then the same process for 1, 2, 3, 4, and 5 follows suit here. So the probability that all 5 of them are success is like a 0.01%. Questions on how that formula was used? I know they did it all for you, but does everyone understand where all the numbers came from? So again, the top number comes from the number of trials. We had 5 trials. The bottom number comes from how many trials there were minus how many you want to be successful times how many you want to be successful factorial. And then the probability of being success raised to how many you want times the probability of failure raised to how many you don't want. Basically, in this case, I want all of them to not be a failure. Wait, well, I want all of them to be a failure. So not a failure. So, okay. I don't know. Words hard. But questions on that. All right. So then to answer the questions that follow, to find exactly 3 successes, I would then just take my result from right here, which is going to be 3.2%. At least 3. So that means that's 3 or more. You would have to find your probability of 3, probability of 4, and probability of 5, and then add all 3 of those results up, and you get a 3.5% probability of success. What's flipped? Oh, because it's making you find the complement. So that's fine too. It just depends on how much you have to add. So like, I don't know. If this was like 30 different options or 30 different trials or whatever, and I wanted to find at least 2, right? I don't want to go 2 plus 3 plus 4 plus 5. It's a lot easier to figure out 1 and then subtract that from 1. So you don't always have to do the complement where you do 1 minus the result. It just depends on how much data there is to actually add up. At most 2 here, that would mean 2 is the max. So I would have to add up what my result for 2 is, or 1 is, and 0. So I'd add up these 3 numbers here. And when I do that, I would get the success of at most 2, which is a 96.45% that I'll have at most 2 successes. Questions, concerns, thoughts? All right. Too bad they did all that work for us. The next one, they did not. So let's look at example 13. Probably, oh, we'll get to that part later. So probability of too much concern. So in a survey, 3 of 4 students said the court showed too much concern. I don't even know what that means. Is that a law thing? Or in law? Anyone in law? Is it too much concern a thing? Is that a bad thing in court? I guess you got to be non-biased, huh? Oh, gotcha. Okay. Interesting. So, okay. All right. That's crazy. What if, like, I know you're innocent, but I'm a couple of numbers off, so I need you to be guilty. Like, that's just, that's crazy. All right. So, okay, so we're going to find the probability that at most 3 out of 7 randomly selected students will agree with this statement. So either they agree that 3 of 4 students said the court showed too much concern, and we just want to find the probability that at most 3 out of 7 randomly selected. So this is the same. Too much concern. They either agree with that or they don't. This is the probability, apparently. There is your trials, 7 random people, and they either agree or they don't agree, and they want at most 3. All right. So to work out this stuff, we have our n, which would be 7, our x, which would be 3 at most. So that'd be 3, 2, 1, and 0. So we'd have to find all of them, which I think is where this chart's about to come into play. So it'll do a lot of the math for us. What else do we need? Oh, we need to know the probability of success. What is the probability of success here? 3 of 4 said that it was. So that'd be 3/4 or 75 cents. 75 cents. 0.75. The probability of failure would be 25% or the 1/4, right? That one kid said, I don't think they showed too much concern. Right. So we're trying to find the probability that we'll get that probability out of the 7 random. So to plug this in, we'll just calculate it. This will be 7 factorial. Divide it by, if we do the first one, so this will be 3. So we'll do x minus, so 7 minus 3 factorial, 3 factorial, times my probability of success, which is 3/4. I want that to be 3 times 1/4. You could do the math here if you wanted to and say 7 minus 3 or just say 4. These numbers up top need to add up to as many trials that you have. So if you're getting something way off, make sure you go back and check it. And then you would calculate that number. Now, if you look at the chart, I wish there was a way I could save that. Maybe I can. Ignore all the orange that's on the screen. All right, so here's that table. This is actually in your textbook. I know you haven't actually physically opened up the pages because they're still pretty, some of them are still stuck together. So unloosen them, make it pretend like you looked at it. It's great stuff because we spent some good money on that. All right, but here's a table right here. So the N here is how many is in your trial. So I need to drop down. I need to drop over here to where my trial is. I'll go ahead and delete this. So I have 7 trials. So this is the numbers I have. They got a lot more in there, and you can see that in your book. I believe they say that's in your appendix A, table B. So that's going to be in the back of your book somewhere in your appendix. All right, so here we go. So here's your probability of 7 events happening. And on top, it has your probability of success. But they only go by 0.1, 0.2, 0.3, 0.4, 0.5, 0.6. We're allowed to estimate. I don't think they're going to let us do it. Because I need 0.75, which will be not available. Yeah, so like if this was like this right here is 0.05, 0.1, 0.2, 0.3, 0.4, 0.5, 0.6, 0.7, 0.8, 0.9, and then 0.95. Because obviously if it's 0, it's 0. If it's 1, it's 1. And then we want at most 3. So here's 3 right here. So we would go to 1, 2, 3, 4, 5, 6 right here. But we need really and truly in between here. And that's the issue. Because the odds aren't just 7.7. Well, that stinks. They give us this nice chart. We can't even use it. All right. Well, in that case, handy dandy calculator it is. I would definitely use an Inspire for this one. Your blue ones aren't going to be able to handle the calculations. All right. So I'll try to do this all in one clean motion. So we need at most 3. So we need it 3, 2, 1, and 0. So if we start off with 3, that would be 7. factorial over 7 minus 3 is 4 factorial times 3 factorial. And make sure they put it times there. Probability of success was 0.75. We're going to raise that to we want 3 successes times 0.25. We want 4 failures. There's our first result. Copy paste. 7 minus 2 is now 5. 2. 2. 5. Enter. Copy paste. Copy paste function is really nice, guys. 6. 1. 1. 6. Last one. All right. And I want to take this plus this plus this plus this last one. And there's your odds. Power of the calculator. So the answer there is then 0.07, we'll say to 3 decimal places, and we'll say 0.071 or 7.1%. Right? That you'll find at most 3 kids that will agree with this statement. Any questions on that? So had you had some probabilities of success that were nice, even 0.05, 0.1, 0.2, 3, 4, 5, 6, 7, 8, 9, or 0.95, then we could just use this chart here. And I could just selected the options I wanted and then added them up or added them down, depending if it was at most or at least. So maybe on the homework, you might have some of those. All right, let's look at example 14, where it says the probability of wanting a toy. Looks like we actually could probably use this chart now. So if 20% of children were reported to want a particular toy, use the table above to find the probability. So we got that nice even probability of 0.2. So this will be your probability of success will be 0.2. Probability of failure would be what? 0.8. Let's see. Okay, so it looks like 7 is our trial. So that would be our N. And then each one of these would be my X values for my samples. All right. So I'm going to try to use the chart here as best I can. I think it breaks it down for you on the next page. I guess not. Oh, well. All right, I'm going to go to the chart to kind of help you through this. And then you can just write down all the stuff underneath that. So we have 7 trials. So again, I'm going to go back to the bottom here. And then to write out some results here. This was if the probability was 0.05, 0.1, 0.2, 0.3, 0.4, 0.5, 0.6, 0.7, 0.8, 0.9, and 0.95. You do not have to write this down. I just can't get the whole column on there. I care about this, because that is my 0.2% of success. So if the first one says exactly 4 out of 7 children want a toy, I would go right here to 4. And 0.029 would be my answer. Questions on that? I happen to do the math. Now you could do the math and still get the same answer, but this chart's kind of nice and handy. I may maybe print a copy. We might be able to utilize this on the test. So make sure you know how to utilize it, or you can use the formula. We'll see. The next one was at most 3. So at most 3 tells me 3 or less. So here's 3. So that means I need to add up all of these numbers. So when I do that, I get 0.210 plus 0.367 plus 0.275 plus 0.115. So what is it? There we go. So to get at most 3 children that want a toy, you pretty much have a 96.7% probability, which makes sense, right? Every kid wants a toy. Then the last one, at least 4 of the children. So what's at least going to do? Good. It's going to be that number or more. So 4, 5. I guess I'm thinking what's going on here is the number is so small it's insignificant. So this is like probably 0.000.000 is my assumption there. Let's calculate, see how close we are to the answer. So 0.029 plus 0.04, and that's it. And that's exactly what, yeah, that's exactly what they said. Those blanks is that the probability of that happening is so insignificant, it won't affect your probability at all. So any questions on how to use the chart? Again, the chart is only useful if your success rates are one of those percents. So like earlier, when we had the 0.75, we were not able to use this chart. Good. All right. So yeah, I think I might make that a test question and then give you a chart and see if you're able to use it. All right. So in example 14, it's not, oh, we just did that one. All right. So objective 4, we're going to find the mean, variance, and standard deviation for the variable of binomial distribution. Is there only 3 sections in Unit 5? There's not a 5-4? Well, that's what's open. I think there's a 5-4. I think this starts 5-4. Nope, you're right. There's only 3. I don't know if I'll finish this. I was thinking that was a 5-4. All right, anyways. All right, so the mean, variance, and standard deviation for a binomial variable can be found using the methods of any probability distribution, but there are shorter mathematically equivalent formulas for the mean, variance, and standard deviation. So basically saying you can calculate it with the same formulas you've always used, so you don't have to memorize anything new, but there are simple formulas to use if you know it's binomial. So if you know it's binomial, to find the mean, you can literally just take your n, how many samples there are, times the probability of success. And then you're done, right? Or you can work out all the work. To find the variance, you can take the number of samples or number of trials times the probability of success times the probability of your failure, right? Because that's what your Q is 1 minus P. And then that right there would give you your variance. And then to find standard deviation, you just take the square root of that, and that would give you the standard deviation. Right? So again, you can either memorize these new quicker formulas, or you can still do the same process of finding your regular mean and variance and standard deviations. Right? So again, these formulas do become helpful, but they're only good for binomial experiments. So either that means only 2 type of answers. It either is or it is not. Any questions there? Right? And that works really good with large trials. So if you have like 100 trials, you don't want to have to be doing that success rate for 100 different things. All right, so let's look at an example, which they did not quite do it all. Okay, cool. So for a binomial distribution, so it told us what it is, and it typically does. It will say it's in bell shape, unimobile, bimobiles, just to give you, or normal distribution, also known as bell or unimobile, for which there are 500 trials. So I don't want to have to go find the mean of 500 different successes. And the probability of success is 0.25. What is the mean, variance, and standard deviation? So using these quicker cuts, I can literally just go 500 times 0.25. Yes. That's basically turn that into $5. Yeah. So 125 would be your mean. Makes sense? Okay. So then the variance, you already calculated that mean part. So that's going to be 125. Oh, I lied. It is N times P times your failure, which in this case is 125 times 0.75. So you do it in your head or use a calculator. Doesn't matter to me. Close. So 93.75 for your variance. And then I can just take the square root of that. And now I have my standard deviation, which was 682. Questions on how to use the new improved fancy formulas? On a side note, because this is where my brain goes, I was studying up for preparing to do this class again for the college kids at Lamar, and I figured out the shortcut for variance and standard deviation when dealing with sample. Like at first, it just looked like it was more work, but it's actually a lot quicker. I get it now. Yeah. So I get now why y'all might want to use that on the homework. At first, I was like, man, it seems like there's more going on, but you don't have to do any subtracting. You just literally square all the numbers, add it up, times n, minus square of all, add up all the results, subtract those two, and then divide by n times n minus 1. I was like, okay, I guess. Because that takes out like 2 steps. You don't have to do the x minus the mean, get all those, then square those results, then add those, and then divide. I don't know. Both of those seem just as fine, I guess. I don't know. We did that one. Okay, so example 16. Says 32% of adult internet users have purchased products or services online. For a random sample of 200 adult internet users, find the mean and standard deviation for the number who have purchased goods or services online. So here you go. This is a binomial distribution. So they either did or did not. There were 200 trials. We're going to find and a probability of success was 0.32. There are a fixed number of trials. What are they? 200. Very good. Each trial has 2 possible outcomes. What are they? All right. You bought something. Or you didn't. Each trial is independent. Yes or no? Yes, right? They either did buy something or they didn't. It did not affect the other. The next question says the probability of success remains the same for each trial. What's the probability of success? 0.32 right there. There's your probability of success. Then it says the mean, and I didn't want to erase. So the mean of the number of adult users out of 200 who have purchased products or services would be what? So how would I calculate the mean? Yeah. To verify. Yep. What was the next question? All right. Standard deviation or variance? Or does it matter? Okay, so standard deviation would then be the square root of 64, because that's your n times your p, times your success rate, which was times your failure rate, which would be 0.68. So whatever that is. So 64 times 0.68. That's an 8, by the way, not a 4. And then we hit enter. So it gives us the answer. And then take the square root of that. So we get a standard deviation of 6. I'd probably just say 6.60. Right. And you can go as far as you want with that. I'll do one more or a couple more examples tomorrow. I probably won't record it. But if you want to catch those notes from somebody, please do so. But it's going to be the same concepts as what we just been doing. And then the rest of the time will be for homework. So if you haven't had a chance to do it, if you're here,